Okay, we are going to do friction and resistance and carrying out an investigation. Okay, I'm going to go through how to carry out an investigation, just in case you've got to write one up in your class. So let's introduce friction first of all. Friction is a force that tries to stop objects sliding past each other. It's a contact force, okay, and it must be overcome when you're pushing an object, okay. So pros and cons are, in terms of, look here, motion, turning, gripping. So if I grip something, I need a bit of friction to hold it. Okay, and turning, well, I need a bit of friction between what I'm turning and what I'm trying to turn with. Okay, generating heat. Right now my fingers are really, really cold because inside of the room I'm recording it's freezing, so this is nice. Okay, braking systems on cars and things like that for motion. Now, the cons are the following here, but what the question says here, can you identify scenarios where it's a good thing and a bad thing? Okay, so these are the pros and the cons, but where would that be good? So cars. Braking is a good one. Cars, turning, really good one because the wheels get friction on the ground to get you so you can turn. Okay, let's go for the cons. Reduces motion. Well, that's air resistance. Okay, for example, is really bad. Not quite friction, but you know, it's a certain type. If you've got to move and you've got too much contact with the ground, if you're a car, then basically that's going to slow you down. So that's not good either. So you need a balance between grip and reducing that motion, okay? And also producing wear and tear on things. Again, car's the best example in terms of the tyres. Now, planning and carrying out an investigation into the factors which affect friction. How do I carry out an investigation? So let's do this. We're gonna see how the amount of sunlight affects a plant's growth, okay? So what are you measuring? What are you varying? Okay, and what are the other factors might you control? And should you change more than one variable at the same time? Well, the answer to that is no. You should only change one variable at one time, and that's it. But let's go through each one of those in turn. Independent variable. The independent variable is the one you, is the one you change. Okay, you're going to change it to different examples. Okay, so if you're testing the amount of sunlight, okay, you're going to change the amount of sunlight. You're going to change how much sunlight you give. Now, there's a really easy way of remembering this. It's called in class, don't mess. Okay, so in class is independent change, and we'll talk about that in a minute. And the D and M is dependent measure. So dependent measure. So it's the one you measure as a result. So in this plant growth experiment, okay, it might be the number of leaves, it might be the height, okay, for example. But it's in class, don't mess. That's the best way of reminding yourself. And that means independent change and dependent measure. So the independent is the one you're going to change and the dependent is the one you're going to measure. And when you do graphs, the one that you are changing, the independent goes on the x-axis and the dependent goes on the y. Okay, and we'll talk about that later on when we show you a graph. Next thing is the control variables. These are the ones you keep the same. And in questions, there's loads of questions and loads of examples where you have to keep control variables the same and they try and tell you what are the control variables. Now, the control variables in this experiment is the amount of water, the type of soil, the temperature. Okay, and often it is temperature that you keep the same in a lot of experiments. Okay, so if you don't know the answer, just say temperature on most experiments. Now, collecting the data. Data should always be collected in a data table. Okay, and you should always give it a heading. Always use a ruler. Don't do it without a ruler. Okay, the number of students who don't do it without a ruler is huge. Okay, the first column heading should be for the independent variable. Okay, and the next should be the dependent variable. If there are units in the column heading that you do not, if the units are in the column heading, you do not have to put the units on every single value, and we'll show you an example of that. And be consistent with the number of decimal places or significant figures you have, and we'll show you an example of that now. So here you have, I've got centimetres here, so I don't have to put centimetres all the way down here. Centimetres here, don't have to put it all the way down here, and centimetres here, don't have to put it all the way down here. So none of these need the centimetre mark. And they've all got one decimal place, as you can see, as well. Graph plotting. What kind of graph are you going to plot? So if it's a bar chart, okay, it uses something called categoric variables. So they're basically words and not numbers, okay? So not numbers, words, descriptions, and things like that. So if you're choosing between a brown-haired person and a blonde-haired person, that's a categoric variable, and that would be a bar chart. Best fit graphs. When we plot points and draw on a line of best fit, that's the most often one. That's the one we use in almost every scientific example. Okay, and that's to do with numbers. Scatter graphs. no clear pattern, and that is usually used not in scientific stuff at year 9 or GCSE, okay, or even A level. The best fit graphs is where you need to go. So you need to make sure what goes on the horizontal axis and what goes on the vertical axis, and remember the independent variable goes on the horizontal axis, which means the dependent variable goes on the y. Work out scale. The scale must be more than half the axis. Basically what that means is it must fill at least half the paper that you are given. At least half the paper that you're given. Okay? And that's really important. Don't make it small. And if it's done perfectly, the scale should fit the entire page. Okay? And each square must be the same value, and do it in pencil. Label each axis with the name in units and do that in pen. Plot the point with an X, never with a dot. Never with a dot. Okay? Do it with an X. Now, if there is a clear pattern, draw a single best fit line, and we'll show you an example of this in a minute. And there'll be similar, this is really important, there should be a similar number of points on each side of the line. It does not have to go through each cross. It does not have to go through each cross. It just has to do the general trend, and it has to be with the same number of marks on either side of the line. Draw the line in pencil, just in case you get it wrong, and you can go over it and remove it and then go over it again. Now, here is an example here. So can you see that, first of all these crosses are not necessarily on the line itself, but there is a similar amount of crosses on either side of the line. It follows the general trend. You can see I've got my units down here, and this is time is the one I'm changing on this one, for example, and then the volume is the one I'm measuring, okay, on this one. And you can see that that is a good line of best fit. Now, also a good rule is, if your experiment you're doing has 0 on the x-axis at the same time as 0 on the y. So, for example, if I'm doing an experiment and I'm measuring the time and I know that there'll be no gas at 0, then I should start it from 0. That makes sense. Now, writing an experimental plan, it's good to have a plan sheet like this that you can see. So what's the aim? What's your hypothesis? What's your prediction? That should be based on some science. What's your apparatus? What's the safety concerns? And what's your method? And a nice label diagram is always good. A good table that goes over there, and labeling all of your variables is good practice for. And you can use this if you want. Just stop the video, take a copy of this, and you can write out a few of these different experiments with this in mind. Now, conclusion. You've got to then say, what are the results? Describe the trends in the results, whether there's a positive trend, whether it goes up, whether it slows down, and make a comment on the slope on your graph. So if the slope has decreased because you have a line that goes and then flattens out, say that the gradient is decreasing until the gradient is horizontal. Okay? And then explain those results with as much science as you can. Okay, that's a general way on how to write an experimental plan, but the only way you can do this and really get it into your head is if you do it in class or you do it yourself.